Sources with periodic waveforms. In circuit theory, sources with periodic waveforms refer to energy sources that provide electrical signals that repeat at regular intervals. Unlike DC sources, which deliver constant voltage or current, periodic sources vary over time and exhibit a repeating pattern. These are fundamental in AC circuit analysis and are critical in various applications, such as power systems, communication systems, and signal processing. Types of periodic waveforms. Periodic waveforms can take several forms, each with distinct characteristics. Sinusoidal. The most common and fundamental type of periodic waveform. It smoothly oscillates, following a sine function. It is characterized by a smooth and continuous wave. Mathematical representation of sinusoidal wave is done through this equation. Square wave alternates between two distinct levels, spending equal time at each level. It has a rapid transition between high and low values, producing a blocky waveform. This is the mathematical representation of square wave. Triangular wave linearly rises and falls, forming a triangular shape. The waveform has a uniform slope, making it appear like a triangle. A triangular waveform can be represented as a piecewise linear function, or using a Fourier series. Mathematical representation. This is the mathematical representation of triangular waveform. For a triangular waveform with amplitude A and period t, starting at t equal to 0. Sawtooth wave rises linearly and then drops sharply. It resembles the teeth of a saw, hence the name. The waveform ramps up and then drops back to its initial value. Mathematical representation. This is the mathematical representation of sawtooth wave. For a sawtooth waveform with amplitude A and period t, starting at t equal to 0, and assuming a linear rise, followed by a sudden drop. Properties of periodic waveforms. Understanding the key properties of periodic waveforms is essential for their analysis. Frequency. Frequency is the number of cycles the waveform completes in 1 second. It is measured in hertz. Frequency determines how fast the waveform oscillates. Period. Period is the time the waveform takes to complete one cycle of the waveform. It is measured in seconds. It is the reciprocal of frequency. Amplitude. Amplitude is the maximum value, peak, of the waveform, indicating how strong the signal is. Phase angle. Phase angle represents the shift of the waveform relative to a reference point in time. It is important in AC circuits, where waveforms may not start at the same point. Harmonics and Fourier series. Periodic waveforms can often be decomposed into a series of sinusoidal components, known as harmonics. This concept is critical for understanding non-sinusoidal waveforms. Fundamental frequency and harmonics. The fundamental frequency is the lowest frequency component of the waveform. Harmonics are integer multiples of the fundamental frequency. For example, if the fundamental frequency is f, the second harmonic would be 2f, the third would be 3f, and so on. Non-sinusoidal periodic waveforms, for example, square, triangular, can be represented as a sum of sinusoidal functions using Fourier series. Applications in circuit analysis. AC analysis. Periodic waveforms are integral to AC circuit analysis, where sinusoidal voltages and currents dominate. The analysis often involves calculating root mean square values to determine effective power and voltage levels. Signal processing. Engineers use periodic waveforms to encode information, such as in modulation techniques, where information is transmitted over carrier signals. Power systems. Most power systems operate on sinusoidal AC voltages, for example 50 Hz or 60 Hz, because of the efficiency of generation, transmission, and transformation. Conclusion. Understanding sources with periodic waveforms allows engineers to design and analyze circuits involving AC power, communication signals, and control systems effectively. For more educational videos, don't forget to subscribe to our channel, Eduzon Academy.